Hello everyone, Michael Pierce here. You will notice that this is not a Zarathustra video. The series is still ongoing. I just did not really have the script ready for today, and that is in part because, as I think I mentioned in the video last week, I did my master's thesis defense this week on Wednesday, and that went very well, all things considered. And I've decided that I would like to share my thesis with you. So this is not going to be perfectly word for word read, because I will probably interject a few comments here and there, in part inspired by some of the questions that occurred during the thesis defense. But I just felt like this would be something I'd be interested in sharing. So a complete shift from talking about Zarathustra to talking about philosophical issues in quantum mechanics. So I hope you enjoy it. Hope you find it interesting. And here we go. The title is To Be or Not to Be, a critique of scientific anti-realism in the context of single-photon interference. Quote, "By assuming it a duty to seek what is not known, we shall be better and manlier and far less unproductive than if we assume that what we do not understand cannot be nor is our duty to seek." Unquote. That is Plato from the Meno, 86b through c. 1. Introduction. In a 2008 editorial for the American Journal of Physics, respected physicist Nico van Kampen railed against, quote, "the scandalous fact that 80 years after the development of quantum mechanics, the literature is still swamped by voluminous discussions about what is called its interpretation," unquote. This, in spite of the fact that, according to van Kampen, quote, "quantum mechanics provides a complete and adequate description of the observed physical phenomena on the atomic scale," unquote. That same year, physicist Art Hobson responded in an editorial for the same journal. He readily concurred with Dr. van Kampen, albeit with the request that van Kampen quit speaking of the wave function and refer instead to manifestations of a matter field. 5 years later, in 2013, Hobson elaborated on his own views in an article titled, "There Are No Particles, There Are Only Fields." This, in turn, elicited that same year an editorial from physicist Robert Sciamanda. He commended Hobson's efforts, but pointed out that, quote, "by extending some of Hobson's ideas, I arrive at the conclusion that in addition to there being no particles, there are not even fields," unquote. For, like particles, fields are only, quote, "a most useful calculational model, doing little or nothing to identify a model for the ontological reality of the entity being described," unquote. Needless to say, the vehemence with which some physicists decry the perpetual controversy over the interpretation of quantum mechanics itself suggests the warranty of the controversy, the roots of which must run deep to resist 80 years of orthodox efforts to remove it. Pablo Raba, 2013, suggests that the roots run as deep as the virtue of curiosity. It is indeed bitterly ironic that this virtue, the desire to know, to which every physics department owes its undergraduate enrollments, becomes more and more a vice the further a student ventures into the field. And in fact, one need not venture very far to at least glimpse it. As early as 1978, Dr. Robert Garrock began his popular science book, General Relativity from A to B, with a remarkable declaration, quote, "Physics does not, at least in my opinion, deal with what is real. or with what something is really like. The reason, I suppose, is some combination of 1. One does not know how to effectively attack such questions. 2. One does not know what sort of thing would represent an answer. 3. These questions are too hard. In any case, one conventionally deals with relationships between things which one does not, or perhaps cannot, understand on a deeper level." Unquote. Gerach is not alone in this opinion. Scamanda, who I quoted before, concludes his editorial against Hobson in a similar spirit. Quote, "Perhaps there is no useful conceptual model to describe ultimate reality in human terms, and perhaps there is no need for one." Unquote. Walter Isaacson, in 2007, in his introduction to Einstein and Infeld's The Evolution of Physics, summarizes the climate of opinion surrounding the birth of quantum mechanics. Quote, "Einstein's great dispute with the Bohr-Heisenberg crowd over quantum mechanics was about reality. Did it exist? More specifically, was it meaningful to speak about a physical reality that existed independently of whatever observations we could make?" Unquote. He adds, quote, "Bohr and his adherents scoffed at the idea that it makes sense to talk about what might be beneath the veil of what we could observe. All we could know was the results of our experiments and observations, not some ultimate reality that lay beyond our perceptions." Unquote. Just as a little side note, I have a hard time imagining Niels Bohr truly scoffing at anybody, but I could see his adherents doing it, so I'm a little defensive of Bohr, even though I disagree with him fairly strenuously in this paper. In current philosophical terminology, Einstein and Bohr would be classified as realist for Einstein and anti-realist for Bohr, respectively. I am here following Chakravarti from his 2017 article, who gives for possible sufficient conditions of realism a, quote, "the metaphysical commitment to the existence of a mind-independent reality," b, "the semantic commitment to interpret theories literally or at face value," and c, "the epistemological commitment to regard theories as furnishing knowledge of both observables and unobservables." Unquote. Anti-realism involves the rejection of at least one of these three forms of realism: metaphysical, semantic, or epistemological. Within the debate between realism and anti-realism, Chakravarti further differentiates between arguments concerning the actual achievements of science, whether a scientific theory has actually achieved a correspondence with reality, whatever that is taken to mean, versus the proper aims of science, i.e., whether scientific theories should even aim for such a correspondence with reality. The present paper is an apology for maintaining the aims of metaphysical and epistemological realism in the context of a specific but central quantum phenomenon, single-photon interference in the double-slit experiment. This specificity is meant to ground my reasoning firmly in experimental fact. However, this does not necessarily preclude a more general applicability of my commentary to other domains of quantum physics because, as Richard Feynman put it, the double-slit experiment, quote, "has in it the heart of quantum mechanics. In reality, it contains the only mystery of quantum mechanics," unquote. The double-slit experiment was originally used by Thomas Young to demonstrate the undulatory or wave nature of light by showing how light is capable of self-interference, just like waves of sound or of water. However, in the 20th century, Albert Einstein demonstrated the particulate or quantum nature of light. This wave-particle paradox is most clearly seen in a version of the double-slit experiment where the light beam is filtered so that only single quanta of light, i.e. photons, pass through the apparatus one at a time. Nevertheless, they build up an interference pattern in the aggregate, like a pointillist painting by Georges Seurat. Thus, to a degree unprecedented in classical physics, it is unclear what ontology could possibly underlie such a phenomenon. No classical model, neither wave nor particle mechanics, is adequate to describe the total phenomenon of single-photon interference. To use the terminology of John Bell, the nature of the quantum beables, the ontological objects of study, remains mysterious. A traditional and popular solution to this mystery is to reject it altogether, that is, to reject the ontological problem of single-photon interference and of quantum phenomena generally. Contemporary philosophers recognize this rejection as an anti-realist stance. However, it should be kept in mind that the terms realism and anti-realism are not in wide usage among physicists, likely because, writes Chakravarti, quote, "it is perhaps only a slight exaggeration to say that scientific realism is characterized differently by every author who discusses it, and this presents a challenge to anyone hoping to learn what it is," unquote. Philosophers must beware of making Procrustean impositions upon physicists, especially when the beds themselves are of varying sizes. On the other hand, there is some evidence that the terminology is catching on, as it were. For instance, one of the more noteworthy experiments involving Bell's theorem, published by Groblacher and Zeilinger et al. In 2007, declared itself an experimental test of non-local realism, and exposited that, quote, "most working scientists hold fast to the concept of realism, a viewpoint according to which an external reality exists independent of observation, but quantum physics has shattered some of our cornerstone beliefs," unquote. My argument may be organized under two heads, corresponding to two of the three types of anti-realism identified by Chakravarti. One, a critique of metaphysical anti-realism, which denies the existence of quantum beables, in this case photons. Two, a critique of epistemological anti-realism, i.e., that which denies the knowability of quantum beables. I have a footnote here that's important to read. I do not address Chakravarti's third type of realism, semantic realism, which entails a, quote, "literal interpretation of scientific claims about the world," unquote. In other words, semantic realism assumes a direct correspondence between human descriptions and their objects, so that propositions like E equals mc squared have a truth value connected to definite states of affairs in the world. Semantic anti-realism would be the negation of this claim. To address semantic anti-realism would entangle my argument in complex questions of reference that are tangential to my purpose. My concern is whether there are beables apart from observables, and whether these can, in principle, be known. How to establish linguistic relations between us and them is an important but separable question. End footnote. So, of the two versions I gave, metaphysical anti-realism and epistemological anti-realism, metaphysical anti-realism rejects the question of ontology outright, while epistemological anti-realism accepts the legitimacy of the question but denies the possibility of answering it. I argue that neither of these approaches successfully evades the problem of ontology in single-photon interference phenomena. It is important to note at the outset that anti-realism, at least as I treat it here, is distinct from what I will call ontological agnosticism. The genuine anti-realist, whether metaphysical or epistemological, makes a positive claim of the non-existence or unknowability of quantum beables, using John Bell's terminology again. The agnostic refrains from making any such positive claim. They simply say, I do not know anything for certain about the quantum beables. This matter remains underdetermined by the available evidence. In principle, the agnostic is open to the establishment at some future time of a satisfactory realism concerning quantum beables. An alleged anti-realist who is open to such a possibility is not, under these definitions, a thoroughgoing anti-realist, but only a fair-weather anti-realist, which is to say, an agnostic. For the thoroughgoing anti-realist says either, I know that quantum beables do not exist, or it is impossible for us to know anything about quantum beables, both of which are strong positive claims. This distinction between anti-realist and agnostic will bear repeating in the discussion of epistemological anti-realism in section 2.2 below. This is me talking outside the essay, this was a point of some confusion. I don't want to say contention because that's too strong, but the way that I use anti-realism is, I suppose, a bit unfamiliar to how many philosophers use it. I make use of the term in the way that I do to make this strong positive claim because that is the kind of claim, as we shall see, and as we've already seen a little bit, physicists have been making. And in some sense, I am trying to correct what I think is a deeply incoherent position that physicists have quite clearly stated is their position. They say things like, there is nothing there. And we're going to see some of the more obvious quotations of that in a bit, which is a positive claim. But most of the philosophical anti-realists that I am aware of, they don't make that claim. They are agnostics, which in my mind, in some sense, why would you call yourself anti-realist? You're just a realist who hasn't settled on what you think is real yet. But as long as you are open to the possibility that we can get to some reality, then in my book, you are an agnostic. You're not an anti-realist, and it's anti-realism that I am attacking. The anti-realist says either there isn't anything there, or there might be something there, but we can never know. And so those are the two positions I'm attacking. So it's interesting in talking with John Barnes about this, actually. He pointed out that in some sense what I'm really doing is I'm attacking an attitude. I'm attacking a kind of zeitgeist that has been present in quantum mechanics for a long while. And it can be a bit tricky attacking an attitude, but this is my attempt to do so. So, to return to the paper. With that in mind, I shall outline the present paper. I begin with a description of single-photon double-slit experiments, both in general and in a specific instantiation developed by Ruckner and Peidel in 2013 for public demonstration. I will read a little footnote here. I have chosen this particular version of the experiment because it is explicitly developed for pedagogical purposes, such that the technical particulars of its construction are more accessible to non-specialists and laymen. But many other single-photon interference experiments have been performed. See, for example, Ruckner and Titcomb from 1996, and Dimitrova and Weiss, 2008, including the footnotes from those papers. In any case, once the experiment and associated phenomena are laid out, I proceed to an explanation and critique of the two forms of anti-realism that I identified above. I'm going to read the general explanation of the experiment. I'm going to either skip entirely or at least abridge the more specific experiment just for the sake of time, because I don't think that will be as useful. We just need to get the general idea. But I wanted to include the much more specific experiment just so that there's no vagueness about what the experimental data is, at least no vagueness that is not inherently there. So, Section 1.1, Single-photon interference experiments in general. Single-photon interference is a phenomenon observed in versions of the double-slit experiment. In a regular double-slit experiment, a laser is shown through a narrow twin aperture, the double-slit, onto a wall where it forms a distinctively striped interference pattern. This pattern is explicable in terms of wave mechanics, where the twin aperture splits the incoming wave into twin waves. These subsequently interfere with each other, alternately canceling and magnifying each other's amplitudes, which results in a striped pattern of bright, dark, bright, dark, bright, dark. The exact form of the interference pattern, depending on the size and spacing of the apertures, the strength and kind of the light source, etc., can all be predicted using the mathematical model of a wave. Therefore, the double-slit experiment initially counted as strong evidence that light, i.e., electromagnetic radiation, is ontologically a wave. However, the matter is not so straightforward. In the special single-photon version of the experiment, the light is heavily filtered so that only a minuscule amount of light leaks through. The back wall is replaced with some form of hypersensitive photodetector. Thus, the filtered light passes through the twin aperture and from there on to the detector, which records the location of the energy that impinges upon it. Remarkably, the detector does not register a faint but continuous smeared pattern, as would be expected from a dimmed-down wave. Instead, it registers a temporal succession of spatially distributed points, or quanta, of energy, i.e., photons. At first, this quantized distribution does not resemble the striped pattern produced by the unfiltered light. However, over time, relative to the filtering of the light, the interference pattern emerges from the chaos, like a dart thrower creating a pointillist portrait of Elvis on a wall, one random dart at a time. The single-photon version of the double-slit experiment demonstrates the particle-wave duality famously associated with quantum physics. The quandary is this: the whole, the wave pattern, is not readily explicable in terms of its detected parts, the individual photon particles. Particles, like those detected by the screen, are localized entities with inertial trajectories, and any number of analogies may be used to intuit the impossibility of mere particles arranging themselves in a wave pattern without some guiding influence. A baseball auto pitcher, for example, or sand grains falling down through an hourglass, or a machine gun, etc. The most obvious problem, to me anyway, is that in the double-slit experiment, the greatest concentration of particles, which forms what's called the maxima of the interference pattern, the central stripe that is the brightest, that concentration of photons occurs in the middle of the screen, which would require a large percentage of the particles in order to make it that bright. A ton of the particles would have to somehow swerve around the central barrier that protracts the twin aperture. In other words, you have a barrier that's splitting the light, but then most of the light ends up directly across from that barrier on the screen. So how are they doing that? Are they going through the barrier? Are they swerving around it? Or is it literally like the wave pattern where effectively the maxima kind of materializes out of the conductive medium? That was all sort of side notes from me. The point is, the whole phenomenon was described succinctly by Bohr in 1949. Quote, "The interference pattern is built up by the accumulation of a large number of individual processes, each giving rise to a small spot on the photographic plate, and the distribution of these spots follows a simple law derivable from the wave analysis. The same distribution should also be found in the statistical account of many experiments performed with beams so faint that in a single exposure only one electron or photon will arrive at the photographic plate. Recent technology has made this phenomenon amenable to public demonstration, as seen in Ruckner and Peitel's setup described below. To paraphrase that setup, it's basically what I explained, but so you can picture it a little bit better in your mind. The point is you have the photographic plate, the hypersensitive plate. I try to go into some detail to explain how that works, but to be honest, that is a slight weakness of the paper that even with the detail I go into, I still don't completely understand, but it has to do with you use what's called an EMCCD, which is an electron multiplying device. So it basically causes like a domino cascade effect. When something as sensitive as a photon hits it, it causes this cascade that you can then detect and record on a screen. It's sort of the basic idea as I understand it. The point is that you have this screen, and the screen will show you the position that the photon was at when it hit the screen. And sure enough, the photons will accumulate, and I'll actually read this part. Ruckner and Peitel's EMCCD sports a pixel grid of 668 by 496 pixels for a total of over 300,000 pixels, which is condensed into approximately half an inch of area. It's pretty incredible. In their experiment, no discernible pattern appears for the first second of exposure, despite accumulating, according to them, over 80,000 impacts evenly distributed on the plate. Only after this threshold does any bias in location begin to manifest itself, and a pattern emerges from the chaos. This, according to the theory, is simply because you have to have enough in order to see the pattern which is technically there. So you need enough photons. I actually did some counting. Let me see. Here we go. In Ruckner and Peitel's setup at 0.1 seconds, with a density of approximately 8,300 impacts, no pattern is recognizable. After 1 second of exposure, with 83,000 impacts, a faint interference pattern can be observed. After 2 seconds, 166,000 impacts, the pattern has become quite clear. Obviously, a lot of this depends upon the nature of the filter that Ruckner and Peitel use, and because they're trying to make it amenable to public demonstration, they want it to go quick, but not too quick. So they're letting perhaps more photons through per moment of time than other experiments in the past have done. But this is precisely what makes it so you can literally like show this to people, and you have like a screen up on the stage that's displaying what is showing up on the EMCCD. Anyway. Classical interference patterns are complex, and it is impossible for ordinary particles following linear trajectories to form them in aggregate, much less form different patterns varying with the type of filter, the light source, etc., in mathematical correspondence with wave functions. This duality is represented by Schrödinger's equation, which treats each individual particle in terms of a larger wave function. The wave function represents a wave of probability, mapping where the particle is most likely to appear when impacting the camera plate. Thus, in the same way that 166,000 flips of a coin will reveal the bias of a coin, whether 50% heads or 30% heads, etc., 166,000 photon impacts will reveal the nature of the wave imprinting upon the plate. This mathematical description has been remarkably successful for engineering purposes, but it makes no clear metaphysical claims. Girardi and Bassi in 2020 write, quote, "Quantum mechanics is a theory which is excellent in telling us everything about what we observe, but it meets with serious difficulties in telling us what there is," unquote. Schrödinger himself referred to it publicly in 1951 as a makeshift and an emergency exit, and agreed with Eddington's assessment that, quote, "Schrödinger's wave mechanics is not a physical theory, but a dodge, and a very good dodge, too," unquote. There's a couple of important footnotes that I skipped over. In fact, actually, just the one that's of most importance. It is a common misconception that light shown through a single slit behaves like a particle, whereas light shown through a double slit behaves as a wave, so that the famous wave-particle duality arises because of the experimenter's imposition of different measurement apparatuses, the single slit versus the double slit. This is simply false. Light behaves as a wave in either case. Wave-particle duality is far better demonstrated by single-photon interference phenomena, as we see in Ruckner and Peitel's experiment, where individual localized particles approximate in mass a wave pattern over time. If you're wondering about the single-slit pattern, part of what's happening there is you do still get the interference fringes. It's just that the interference is not as strong or obvious as it is with the double slit experiment. The double slit experiment is impossible, as I understand it, to explain away through particle impacts, whereas there may be some ways you could do it with the single slit. But the reason for those, interestingly, you can also explain them away much better using the wave mechanics, as Max Born writes, quote, "These are due roughly to the mutual interference of the elementary Huygens waves spreading out from the individual points of the slit," unquote. In any case, if anybody's curious, I can go over more of the technical details in the comments, at least to the best degree that I can. But all right, so with all of that as introduction, let's move on to the actual critique. So this is section 2, Critique of Anti-Realism. Philosophical skepticism is common among quantum physicists, so many of whom place the ontology of quantum objects outside the limits of possible knowledge. In 1976, John Bell wrote, quote, "It can be argued that in trying to see behind the formal predictions of quantum theory, e.g. Schrödinger's equation, we are just making trouble for ourselves, that it is futile to try to see behind the observed phenomena. This is, as far as I understand it, the orthodox view, as formulated by Bohr. Many people are quite content with it," unquote. In the context of the double-slit experiment, this means we cannot know how photons form interference patterns, only that they do so. For, quote, "quantum mechanics had to renounce the idea of a classical trajectory," unquote. That is taken from Elaine Aspect, one of the Nobel Prize winners. This is something he wrote in 2004. In fact, actually, as an introduction to John Bell's book, which is kind of funny. There are seemingly irreparable gaps in our knowledge of what quantum objects, like photons, are doing between their generation and their detection. As Bell suggests, this kind of skepticism may be traced back to Bohr and Heisenberg and their principles of complementarity and indeterminacy, respectively, which form the, quote, "common denominator for a variety of related viewpoints known as the Copenhagen interpretation," unquote. That's from Max Jammer, 1974. It is often assumed that the Copenhagen interpretation is only epistemologically anti-realist, consigning all that is experimentally unobservable to the flames of unknowability. However, in Schrödinger's analysis, Bohr and Heisenberg were in fact metaphysical anti-realists. Quote, "The view is ascribed to Bohr and Heisenberg that there is a fully determined physical object in existence, but I can never know all about it. However, this would be a complete misunderstanding of what Bohr and Heisenberg and those who follow them actually mean. They mean that the object has no existence independent of the observing subject. They mean that recent discoveries in physics have pushed forward to the mysterious boundary between the subject and the object, which has turned out not to be a sharp boundary at all, unquote. For our purposes, it is unnecessary to establish whether Bohr or Heisenberg really thought such a thing. What matters is that Schrödinger distinguishes between a denial of the existence of beables and a denial of their knowability, that is, between metaphysical anti-realism and epistemological anti-realism. I begin with the former view, which is the more radical but less openly espoused. Section 2.1, Metaphysical Anti-Realism, i.e., the non-existence of beables. Metaphysical anti-realism in the context of single-photon interference claims that to posit an ontology for photons independent of the experimental apparatus that detects them is folly, simply because there are no such entities. Photons only exist in the experimental context. This context must, therefore, summon them up ex nihilo and clothe them in properties appropriate to the experiment. Quote, "We know by measurement that a mark was created on the screen," writes Tim Maudlin, a philosopher of science. Quote, "We do not know by observation whether it corresponds to an antecedently existing position of the electron," unquote. This is in spite of the fact that, quote, "a measurement is not just any old physical interaction with a system, but an interaction so designed as to yield information about features the system had antecedently to the interaction," unquote. From this, it seems to follow that measurements of quantum objects are not measurements at all, but acts of creation. It must be emphasized that this is not merely an epistemological limitation. It is not that quantum objects are simply unmeasurable by us humans. On the contrary, this kind of metaphysical anti-realism posits that there is nothing to measure in the first place until after the measurement is made. The measurement creates what it measures. The experiment represents a question asked of nature who, being in essence undefined, must invent her answers on the spot by a roll of the dice or a flip of the coin. Physicist John Wheeler in 1989 states this position quite clearly. Quote, "We ask the yes or no question, did the measurement counter register a click during the specified second? If yes, we often say a photon did it. However, we know perfectly well that the photon existed neither before the emission nor after the detection. We also have to recognize that any talk of the photon existing during the intermediate period is only a blown-up version of the raw fact, a count," unquote. This encapsulates the problem identified by Bell when he posited beables against observables. In quantum mechanics, an observable is the value gotten by measuring some property of a quantum system, i.e., something about the system which one is able to observe. In the double-slit experiment, for instance, this observable property is position. The range of possible values which the observable may take when measured in an experiment, e.g., detection by an EMCCD, indexed in terms of their respective probabilities, e.g., the shape and the wave as defined by Schrödinger's equation, is all represented mathematically as a superposition. A beable, on the other hand, represents that which is, presumably, measured. It is that which is able to be, independent of others' observations. Thus, Bell opines, quote, "It should again become possible to say of a system not that such and such may be observed to be so, but that such and such be so. The theory would not be about observables, but about beables," unquote. To the extent that a beable exists, It possesses at every moment definite values for its associated observables, which values are discovered by experiment. Quote, observables are made out of beables, unquote. That's from John Bell. And beables are the bearers of observed properties, not unlike Aristotelian substances as the bearers of predication. Now, to argue that there are no beables at all, but only observables, is just to argue for metaphysical anti-realism. Bell, paraphrased here by Maudlin, characterizes this situation with an analogy where he measures the colors of a colleague's socks every day at work. Quote, if somehow neither sock had any definite color in the morning, if a sock only acquired a definite color some time later, when observed, for example, then the situation would be truly remarkable. Because of the no definite color to definite color transition, one would rightly wonder about the physics of that change, unquote. Indeed, we would be right to wonder. Nevertheless, this situation does not represent a committed and consistent metaphysical anti-realism, for it still posits something that underlies the indeterminate property of color. The shape, material, and location of the sock remain determined in order to host the variable property of color. A consistent commitment to metaphysical anti-realism would require that there be nothing whatsoever traveling between the generator of light and the detecting screen. All that exist are observed values. There is nothing to host these values before measurement takes place. They spring into existence, ready-made ex nihilo, upon the screen, like the old medieval theory of spontaneous generation of maggots in meat. And in fact, even this would not be radical enough, for in that case the marks on the screen still exist, appearing there according to mind-independent laws. These marks, like the spontaneously generating maggots, would now constitute the beables of the theory, and instead of speaking of photons traveling from source to screen, it would be more accurate to speak of light exercising a spooky action at a distance influence upon the screen to make the marks arise, like the full moon inducing lunacy in a population. But a thoroughgoing commitment to metaphysical anti-realism entails a denial of any beables, not simply an acceptance of strange beables. For this would make anti-realism merely a stopgap for realism, e.g., I am an anti-realist about your beables in order to be a realist about mine. Metaphysical anti-realism, if it is not just ancillary to some sort of realism, i.e., if it is to be distinguished from mere agnosticism about quantum beables, it must expand into a global theory of its own. The progression would be something like follows. I begin by denying the mind-independent reality of photons traveling from source to screen. All that exist are the data of the experiment, that is, the marks registered on the screen. So far, I would still be a realist about the data collection equipment and must suppose that sources of light exercise their effects at a distance, without messenger or medium. If I am to be an anti-realist about this as well, I must deny the reality of the equipment and the data. The screen itself does not exist, but is as much an illusion as the photonic marks. In this way, we retreat further and further into a Cartesian solipsism. The universe itself becomes a grand illusion, a phenomenon without any underlying substance, and yet miraculously consistent in its conspiracy to convince us that something really is there, in between the source and the detector, bearing the values one obtains through measurement. Like Descartes' demon, such a view is extraordinarily difficult to formally exercise, since, by definition, every possible outcome of any experiment may be accounted for as nature's arbitrary answer. There are no beables subject to certain conditions or rules for their being. Consequently, there are no limits to nature's self-expression in experimental contexts, for there is nothing to be unveiled, no puzzle to solve, no coherent crime behind the myriad of clues. This implies that before a measurement triggers a collapse, that's the term used, the collapse of the wave function, before a measurement triggers a collapse to a definite value, the quantum wave function, or quantum state, is only a fiction. There is no quantum state, only collapsed classical states, which are created ex nihilo by measurement. The reliability of the quantum state for predicting the probability distributions of photonic and other properties would be unjustified by anything metaphysically real, and the remarkable success of quantum theory, so often touted by popularizers, would be owed to a miraculous series of sheer coincidences. There's a little footnote here worth reading. This same essential point about the miracles, the miraculous nature, was famously made by Hilary Putnam in 1975, albeit in the context of what I would classify as epistemological realism versus anti-realism. He claims that scientific realism, quote, is the only philosophy that doesn't make the success of science a miracle, unquote. There's a whole literature on just that quotation. I suppose that's a little bit of an exaggeration, but I don't get into some of the issues that are brought up there except in a cursory way because they aren't relevant to what I'm, or at least I don't consider them directly relevant to what I'm saying. The counter-arguments to the no miracles argument do not concern the existence of beables, but only the right of a given theory to claim knowledge of beables on the basis of its own success record, which is a different issue from what I'm talking about. Back to the text. In short, thoroughgoing metaphysical anti-realism destroys the very resources which are necessary to explain phenomena, namely the existence of underlying beables which are independent of observation. There's another relevant footnote here. According to Edward Teller, Bohr understood this sort of phenomenalism as a consequence and appeared ambivalent towards it, saying, quote, "You might just as well say that we are not sitting here drinking tea, but that we are all dreaming this," unquote. This story is corroborated by von Weizsäcker. Quote, "Teller suggested that after a longer period of getting accustomed to quantum theory, we might be able, after all, to replace the classical concepts with quantum theoretical ones." Bohr said at last, quote, "Oh, I understand. We also might just as well say that we are not sitting here and drinking tea, but that all this is merely a dream," unquote. All right, section 2.1.1, Bell's theorem. As radical as this view is, especially when put in more philosophical terms, there is experimental evidence claimed in its favor, perhaps most openly by Groblacher et al., 2007. This alleged confirmation is the Bell test, named for its originator, John Bell. The first official Bell test was performed by Dr. Leonard Kasdy in 1972 for his PhD thesis at Columbia University. He writes, quote, "It might seem that it is solely a philosophical question whether a physical quantity has a definite value before it is measured. However, John Stuart Bell has shown that the answer to the question can be verified by experiment," unquote. Bell tests are built upon Bell's theorem, which proves that the probabilities associated with the measurement of physically predetermined systems are different from those associated with systems whose physical attributes are undetermined until measurement. The technical details of any given Bell test are, unfortunately, beyond the scope of this paper. For our purposes, the following conceptual summary of photon-specific Bell tests will suffice. Certain processes, I have a footnote here, the most popular of these processes is called spontaneous parametric down conversion, which is my new favorite band name, which involves shining a laser through a special type of crystal whose internal structure splits the beam into the complementary parallel streams. However, Casday's test made use of positron annihilation, where electrons and positrons are combined in order to produce entangled pairs of photons. I freely confess I don't fully understand what's going on there, but at least where I'm at right now in my career, it is sufficient for me to take their word for it. So, certain processes can be used to generate pairs of photons with complementary properties, such that a measurement of one photon's property is sufficient for deducing the other photon's corresponding property. E.g., one may deduce from the right or left shape of a shoe that its partner is the opposite. So if I find a right shoe, I know that there must be a left shoe somewhere. Such photon pairs are said to be entangled, and their corresponding properties will always agree in this way. What if, then, one measures different properties of each entangled photon? And just to clarify what I mean by that, rather than say, because they're always going to mirror each other, we know that, and we know that experimentally, as far as I'm aware. But they have multiple properties, so why don't we measure one property on one and a different property on the other one? This is where Bell's theorem comes in. It shows that if all of the photon's properties are determined before measurement, so when they're created, they are created as left shoe, right shoe. They're already left shoe, right shoe, and they are left shoe, right shoe as they go off to be measured. That's what's meant there. If that's the case, then apparently the probabilities ruling their experimental expression are limited in a quantifiable way. And in fact, these probability limitations are not respected in experiment. Therefore, the photon's properties must not be determined before measurement, but rather at measurement. There are, as is often said, no hidden variables constraining the expression of photonic properties. There's some controversy over the use of that term, hidden variables. Tim Maudlin is very vehement against it, but I'm just using it to tie everything together. As Tim Maudlin succinctly puts it, quote, Bell showed that there are limits on the strength of observed correlations between entangled particles if one assumes that the outcomes for each possible setting of the measurement device are predetermined. Quantum theory predicts violations of this limit, unquote, and these violations have indeed been reported in experiment, quite a few actually. I do have a footnote here. I'm a bit divided on this footnote because I suspect that this might be a mischaracterization of the Bell test, but I'm going to read it anyway just to provide an intuition of at least what's in my mind and presumably what's in other people's minds. So if it turns out it's wrong, it will still be useful to know that this is the intuition that I had. So that is, consider a physical six-sided die versus, say, a random number generating computer program. There are certain complex probabilities, such as the likelihood of getting a 1 facing up and a 5 facing north, that being the specific way that the die has fallen. There's certain probabilities like that which are constrained by the physical geometry of the die, but there are no such constraints on the non-physical, non-geometrical computer program. This analogy is problematic if taken too far, but it can at least hint at the meaning and purpose of Bell's theorem. Again, at least as I'm understanding it, so I'm just throwing that out there. Tim Maudlin is quick to point out that these findings, the findings of the Bell tests, may be interpreted not as a violation of realism wholesale, but only of local realism. The fact that a photon's properties change upon measurement can be preliminarily explained by the immense sensitivity of quantum objects to the kinds of interactions necessary to measure those said properties. What is far more remarkable is that when one photon's properties are determined by measurement, the corresponding property in its entangled partner will always be found to agree with it. In other words, quote, interacting with one photon can somehow not merely provide information about the other, but actually seems to affect the physical state of the other, unquote, regardless of their spatial separation at the time of measurement. And this effect is instantaneous, meaning it breaks the cosmological constraint represented by light speed, implying that it propagates without a spatiotemporal medium. This may be taken to imply that, although there are no local, that is, spatiotemporally proximate, variables constraining the photons, there may be non-local variables at play. In other words, one still has recourse to a non-local realism. And this position has been developed by a number of physicists and philosophers, for example, David Bohm, Girardi and Bassi, Tim Maudlin, and William Simpson. However, Groblacher et al., 2007, warned that, quote, the measurement data of their Bell test can neither be explained by a local realistic model nor by a considered class of non-local models, unquote. Said considered class of non-local models would preserve a number of intuitive concepts, which apparently include Aristotelian logic, counterfactual definiteness, absence of actions into the past, or a world that is not completely deterministic. And thus, any non-local extension of quantum theory has to be highly counterintuitive, unquote. In other words, realism sans locality loses its appeal, but realism plus locality is inconsistent with the experimental data. Be all of this as it may, in neither case is metaphysical anti-realism genuinely proposed or metaphysical realism genuinely attacked. First of all, the Bell test only proves, to the extent that anything can be definitely proven in science, that quantum beables are strange, not that they do not exist. Specifically, it proves that quantum beables have a curious property of indeterminacy under conditions of entanglement. This has ready classical analogies. A spinning coin, for instance, is neither heads nor tails until it is interacted with, at which point it snaps to one or the other value. The coin's indeterminacy is not grounds for its non-existence. On the contrary, its indeterminacy in one dimension is only possible through its determinacy in other dimensions. It must have a certain angular momentum in order to keep spinning, for instance, and a certain position in order to be found and interacted with. Furthermore, even if the values themselves are truly metaphysically random, and in this sense created ex nihilo by measurement, yet the fact that only these two values may be measured, as opposed to, say, so with the coin, for example, we have heads or tails, but what if we had four options? What if you had chest or backside or something like that, right? What if it was like a dice and it had six options rather than just two? The fact that we can only measure two options in a given case speaks to the fact that the coin itself is not created ex nihilo by the measurement. The coin still exists while it is spinning, for the coin must be structured in such a way that only two values are possible when its spin is interrupted, heads or tails. The very fact that the coin is indeterminate in its face value, heads versus tails, means that it must exist in such a way that a measurement would grant it a face value. It is senseless to speak of measuring whether a coin or a photon has, for example, high or low blood pressure, because it does not exist along that metric or dimension. It does not have, as it were, the meta-properties necessary for it to have the property or to be either determinate or indeterminate in the property of blood pressure. Thus, although a photon may be indeterminate in its polarization before measurement, the fact that it can nevertheless be reliably induced to have a determinate polarization or whatever you're measuring implies a great deal of determinate structure to the photon. The question is not whether there is a photon, but how and what the photon is. To speculate that photons do not exist because they exist in a strange way is self-contradictory. And I should clarify here, one of my colleagues, Jeremy, brought this up, and I want to clarify it, because he proposed a notion of, oh, well, what if there isn't like a photon, but there's like several entities which interact with each other and produce this what we measure as the photon, or something like that. That's totally fine. All you're saying there is, oh, the beable is not this single entity, it's a couple of entities interacting with each other and producing this effect. I'm fine with that. You just need to, demonstrate why that is the case. So I don't want to get mixed up in notions of, oh, well, what if it's, like a property of a wave field or something like this. That's fine. What I'm arguing against is this attitude that refuses to talk in that way and to posit, okay, what are you talking about? I want you to give me a picture so that we can begin testing it and begin figuring out how it works. Anyway. Section 2.1.2, Idealism. In 2007, physicists Lee Smolin and Jeremy Bernstein published a brief exchange in the New York Review over Smolin's article from that same year entitled The Other Einstein. Bernstein asserted, quote, a quantum mechanician like Bohr would say that in the absence of an experiment to determine, say, a particle's position or momentum, these quantities have no existence at all. This is what Einstein objected to. He once walked back from the Institute of Advanced Study in Princeton with the late Abraham Pais. The moon was out, and Einstein asked Pais, do you really believe the moon is not there when you are not looking at it? But Bell's experiments were carried out by Elaine Aspect and others and showed that Einstein was wrong and Bohr was right. I cannot believe that anyone familiar with this would still agree with Einstein, unquote. Bernstein makes quite clear that Einstein was in favor of metaphysical realism and considered this to be the stakes in his long-standing debate with Bohr. Bernstein then says that, quote, Einstein was wrong and Bohr was right, unquote. That Bernstein never explicitly subscribes to the metaphysical anti-realism ascribed to Bohr is typical in modern debates over quantum realism. This is what I've noticed, anyway. The radical implications of thoroughgoing metaphysical anti-realism are only ever implied, and only ever explored in the guise of a dispassionate historical explication of Bohr's supposed views, capped with the assertion that Bell proved Bohr right. It is left to the reader to draw the inference. And I confess that in my own The New Physics series, I kind of did just that at the very end, though I feel like I got a little more clearly into my own interpretation of what the Bell test means. But anyway, that doesn't matter. It is left to the reader to draw the inference. As a footnote, I did mention it is equally typical of Smolin, who represents the realist here, to make the rebuttal that the Bell test does not rule out non-local realism. So this is kind of where the debate seems to be at right now. The anti-realist, doesn't really state their position immediately because they kind of sense that it's crazy. Whereas the realist will say, well, the Bell test only, non-locality is their escape route, you see. The inference in this case that Bernstein was effectively implying is that quantum objects, and perhaps that which is made out of them, are not there unless someone looks at them. Their existence depends upon their being observed. Now, if by observation we mean an interaction with a measurement apparatus, regardless of whether a conscious scientist is present to perceive the measurement's results, then it is misleading to even use terminology like observation, perception, or measurement, since these all connote the involvement of a conscious subject who does that observing, perceiving, or measuring of the object. When two asteroids collide unobserved in the orbit of Saturn, we would not refer to this as a measurement, but simply as an interaction. And presumably when quantum particles were abuzz in the first moments of the Big Bang, their interactions were not measurements either. Section 2.1.2.1 John Wheeler's participatory universe. The question as to the relevance of a term like measurement to fundamental physical processes is really just the question of whether consciousness plays an essential role in the operations of the universe. Would the universe work in the same way if no consciousness was cotemporal with it? Can it even exist independently of observation? The implication of metaphysical anti-realism is that it would not, since there would be no observers to create the universe through their observations. This was the bold approach of physicist John Wheeler, a student of Niels Bohr, who proposed the participatory universe. Quote, every item of the physical world has at bottom, at a very deep bottom in most instances, an immaterial source and explanation, that what we call reality arises in the last analysis from the posing of yes-no questions and the registering of equipment-evoked responses. In short, that all things physical are information theoretic in origin, and this is a participatory universe, unquote. For example, quote, the photon that we are going to register tonight from that 4 billion-year-old quasar cannot be said to have had an existence out there 3 billion years ago, or 2, or 1, or even a day ago. Not until we have fixed arrangements at our telescope do we register tonight's quantum as having passed to the left or right of the lens, or by both routes, as in a double-slit experiment. This registration reminds us that no elementary quantum phenomenon is a phenomenon until, in Bohr's words, quote, it has been brought to a close by an irreversible act of amplification, that is, of measurement, unquote, unquote. So, Wheeler implies, he doesn't just imply, he says, that the photon did not exist during its 4 billion-year trek from the quasar to the telescope. Specifically, it did not have an existence out there. Now, if Wheeler means by this that the photon did not exist at all, then it is unclear how we could ask it yes-no questions or elicit equipment-evoked responses. To whom or what are such questions directed? If there is no photon, then why do we measure photonic phenomenon with EMCCDs instead of with something else? Without a beable that has certain conditions and a nature to its being, all experimental correlations become radically arbitrary, and the experimental apparatus that produces the phenomena, e.g., say, the double-slit apparatus, is no more rational in its operations than the feng shui of a magic circle used for conjuring supernatural phenomena. You just put this here and then chant the right words and boom, a photon appears, right? It's like, no, there needs to be a causal connection here. Science is constrained in its experiments by the fact that the object of its experimentation, nature, has herself a nature which responds consistently to experimentation. Indeed, she is so historically consistent and theoretically coherent as to be amenable to the formulation of models and laws and their application in technologies. She is independent of, but vulnerable to, observation, serving, in fact, as the basis for observation to take place. To deny this and say that nature does not have a nature is to espouse a contradiction and say that nature and all her children, for example, photons, both exist and also do not exist. By the way, this is me talking again. Well, all of this is me talking, both the paper and me, but I just wanted to throw out there, because I don't want people coming away with this. One of the interesting things that I'm up against when writing a paper like this is that you have the realist camp, and those are the people who they want to take anything mystical or sort of more interesting out of science, is sort of what's kind of going on with Tim Maudlin and some of them, though they can't because they have to have non-locality. What seems to motivate the anti-realist camp is this love of the immaterial and this desire for this mystical element to be introduced, which the problem is that I'm kind of on their side with that. I want to re-enchant the universe, but this is not the way to do it. So if I'm sounding to you like I'm one of those who's trying to take away the enchantment from nature and sort of burst this bubble, I don't know if it makes it make a little bit more sense if, rather than talking about like nature, I talk about God, because that's actually a better approximation of the way that I think about these things. It's like God exists and has a nature, and you can ask God questions and he will not give you a stone. If you ask for a fish, he will give you a fish. He will not give you a stone. He obeys laws, and we can argue about whether he's the creator of those laws or not. The fact is that he does not change. He's the same yesterday, today, and forever. So, if you want a more religious angle, that's more of how I think about it to some extent. I guess that does go into the God does not play dice, and then Bohr says, don't tell God what to do, which I love that quote. I'm pretty sure it's apocryphal. It didn't actually happen, but it's a great quote, and I'm actually kind of on Bohr's side there. The difference is that there's still God, and God is rolling dice, and the dice have a nature. You see this important distinction. It's not the same as saying that we are completely cut off forever from having any kind of access to truth, is really what this kind of comes down to. So anyway, returning to the paper, on the other hand, Wheeler may only mean that the unobserved photon does not exist out there in the external world. Instead, it somehow resides in here as a potentiality in the world of the scientists' theories and predictions. It has an existence independent of any individual observer, but its existence is not independent of the community of observers. Wheeler seems to suggest this view in order to answer the question which he himself poses, quote, how does the vision of one world arise out of the information-gathering activities of many observer participants, unquote. He replies, quote, consider instead the view that objective reality is simply an interpretation of data agreed to by large numbers of people. Heisenberg directs us to the experiences of the early nuclear reaction rate theorist Fritz Houtermans, who was imprisoned in Kharkov during the time of the Stalin terror. Quote, the whole cell would get together to produce an adequate confession and helped them, the prisoners, to compose their legends and phrase them properly, implicating as few others as possible, unquote. In other words, Wheeler is proposing a kind of constructivist metaphysics, where the objective side of reality is furnished not by anything external to the observing subjects, but by the very fact of the subjects' multiplicity. Each observer is constrained in their observations by those of their colleagues, and from this manifold of constraints emerges a line of best fit. This is a fine description of the epistemological process of scientific theory formation, but it cannot stand alone as a metaphysical theory for several reasons. First of all, it raises the question of how various subjects' perspectives coordinate if there is no shared external reality to which each perspective refers. Should we not expect each subject to have their own individual dream, playing out independently of the others? why and how are the various subjects sharing the same dream? It may be objected that they do not initially share the same dream, but it is precisely through their intercommunication that such a shared dream arises. But this begs the question as to the means for such intercommunication to take place, namely through a shared medium of an external world, right? You have to say things to other people, and they have to hear that is what you're saying. And we can get into arguments about people misunderstanding each other, but that just reaffirms the point of, if no one can actually understand each other, then how do we have a shared reality at all? Even supposing the issue of a medium, an external, independent, objective medium, could be resolved, it still raises new questions as to precedence. That is to say, when the observations of two subjects contradict each other, what are the rules for the resolution of this conflict and the determination of reality? If there is no outside authority to whom either side can appeal, namely external reality, then on what basis does one subject win out over the other? In other words, which subject has creative precedence and why? By the way, the argument that I just made there, I only realized after the fact that you can find the exact same kind of argument. I shouldn't say the exact same argument, but turn of phrase. In Plato's Theaetetus, he makes a very similar kind of argument in favor of an external reality or a way that things are. So I just thought that was interesting. Section 2.1.2.2, George Berkeley's Idealism. The full import of this problem of creative precedence may be illustrated through a cursory critique of the most famous of the modern idealist philosophers, Bishop George Berkeley. I do not and cannot intend to make a historical investigation of Berkeley's views in all their subtlety. My purpose is simply to highlight the depth of a particular problem posed by metaphysical anti-realism. To begin with, Bishop Berkeley writes, quote, "It is impossible for me to conceive in my thoughts any sensible thing or object distinct from the sensation or perception of it. All those bodies which compose the mighty frame of the world have not any subsistence without a mind, that their being is to be perceived or known, that consequently, so long as they are not actually perceived by me, or do not exist in my mind or that of any other created spirit, they must either have no existence at all, or else subsist in the mind of some eternal spirit. For there is not any other substance than spirit, or that which perceives." Unquote. Applied to quantum theory, we might say that whatever existence quantum particles have is entirely predicated on their being observed. Esse est percipi, to be is to be perceived. All such matter is really a product of mind, thus implying that the mind, that is, the conscious subject, creates the world. In a solipsistic universe, there is no problem with this view. Trouble only arises when we introduce multiple conscious subjects, each creating a shared world through their observations. Inasmuch as their world is shared, it is dependent upon multiple competing causes, namely the different subjects who observe create it, with no clear way to decide disagreements between them. For example, when two conscious subjects observe the same object, say an apple or a photon, to which of the two is that object's existence and determination due? To answer this, Bishop Berkeley replies, quote, "Whatever power I may have over my own thoughts, I find the ideas actually perceived by sense have not a like dependence on my will. When in broad daylight I open my eyes, it is not in my power to choose whether I shall see or not, or to determine what particular objects shall present themselves to my view. There is, therefore, some other will or spirit that produces them." Unquote. So, the object owes its existence to neither of the conscious subjects, because they are ordinary run-of-the-mill conscious subjects. In fact, Berkeley effectively denies that minds create through observation. On the contrary, mind simply observes what is already there. Who put it there and maintains its existence? Berkeley famously answers, God. So, observation does not create objective reality. It is but a private reflection of reality, dependent upon an external world and not vice versa. Berkeley does not deny an external world, he simply makes it dependent upon a uniquely supernal mind, namely, that of God. God's mind is distinguished from our own in that it alone is capable of creation via observation. To put a little footnote in there, thus Berkeley seems to propose that reality is indeed solipsistic, but the solipsist in question is God. Be that as it may, the question remains as to how it is that God's solipsistic dream is shared with our lesser minds. Returning to the text, in fact, Berkeley seems to require that God's mind be of a radically different character from our own. God's observations become public, objective reality, while our observations become only private, subjective realities. Thus, the concept of matter is simply rebranded as ideas in God's mind. As Downing in 2011 pointed out, quote, "This suggests that Berkeley has replaced one kind of dualism of mind and matter with another kind of dualism of mind and idea," unquote. The upshot is that even Berkeley must have recourse to the concept of an external world, a shared public objective reality, which serves as the means of coordinating its various spectators' perspectives. Whether this objective reality is ontologically matter or idea is superfluous from the perspective of metaphysical anti-realism, insofar as both substances are independent of ordinary minds and function as an external world, potentially amenable to passive observation and investigation. Whether it is actually amenable is the question posed by epistemological anti-realism. Section 2.1.3, Conclusions regarding metaphysical anti-realism. To summarize, metaphysical anti-realism is inherently unfalsifiable, since the arbitration of nature could just as well give answers consistent with, for example, Bell's theorem, as she has hitherto given answers in violation of it. Metaphysical anti-realism is, at bottom, a denial that the consistency of experimental outcomes proves the existence of an underlying beable subject to certain laws for its existence, which laws, owing to their consistency, are formulable. It is, in short, an appeal to the problem of induction, i.e., that consistency is no argument. But even if this is so, this cannot forbid our making sense of what nature, with unparalleled consistency, has dreamt up for us thus far. Photons may have a strange, indeterminate nature, but they are also highly consistent in this nature, to the extent that reliable technology has been constructed with quantum objects serving as mechanisms. It is this formulable consistency which encourages us to assume an underlying beable. A dream is still a dream of something. It may be that an evil demon is tricking us, but we might as well figure out the rules of the game that the demon has hitherto played. As Leibniz wrote, quote, "Although the whole of this life were said to be nothing but a dream, and the physical world nothing but a phantasm, I should call this dream or phantasm real enough if, using reason well, we were never deceived by it." Unquote. Section 2.2, Epistemological anti-realism, i.e., the unknowability of beables. Epistemological anti-realism is a far more popular position than metaphysical anti-realism. It holds that there are beables independent of measurement, but that we can only know these beables through the measurement of their observables. To use the terminology of Grover Maxwell, 1962, epistemological anti-realism must argue that beables are unobservable in principle. We might also say they are unknowable in principle. In fact, broadly speaking, the arguments for epistemological anti-realism in the context of quantum theory may be grouped under these two heads. One, quantum beables are unobservable in principle because of practical limitations. Two, quantum beables are unknowable in principle because of theoretical or representational limitations. Before proceeding to a critique of 1 and 2, it bears repeating my introductory distinction between the thoroughgoing anti-realist and the agnostic. The thoroughgoing anti-realist makes a positive claim, either that quantum beables do not exist, metaphysical anti-realism, or that they can never be known, epistemological anti-realism. The agnostic, on the other hand, refrains from making any such judgment and is, in principle, open to a sufficiently convincing realist theory someday coming to light. Again, the epistemological anti-realist makes the positive claim that we can never, and so will never, attain knowledge of quantum beables. This is distinct from the agnostic claim that, as of now, we have not yet attained knowledge of quantum beables. Consequently, the thoroughgoing epistemological anti-realist faces the burden of showing that quantum beables are somehow unknowable in principle and not merely in present fact. This distinction is crucial because my chief purpose is to defend the aims of realism apart from any particular realist theory. Consequently, any anti-realism that is not thoroughgoing in the above sense cannot be of concern in this paper. To curtail metaphysical speculation on the basis of what is currently observable is very different from legislating what is observable in principle. The former sets standards for hypotheses, while the latter prejudices against them. For, often enough, the horizon of possible observation has been extended precisely because people believed first that something really existed beyond our current epistemological horizon, and second, that some means could be devised to extend that horizon, e.g., the telescope or the microscope. The absolute inaccessibility of anything to knowledge must, it seems to me, remain an open question, unless it somehow be defined a priori. But any great readiness to do this, especially in the sciences, ought to arouse suspicion that the would-be Kantian is discouraging curiosity in the interest of dogmatism. Section 2.2.1 Practical Limitations to Observation. The epistemological anti-realist must bar epistemic access in principle. One of the most popular methods for doing this is to identify some insurmountable physical or practical limitation to human observational capacities. This was the chief tactic of Niels Bohr in his long and famous debate with Einstein over the theoretical sufficiency of quantum mechanics, which is to say, the sufficiency of an explicitly anti-realist theory for science. These practical limitations may be grouped under two heads: A, the problem of incompatible measurement apparatuses, and B, the problem of measurement disturbance. Section 2.2.1.1 Incompatible measurement apparatuses. A. Regarding A, Bohr claims that the wave and particle aspects of light are, quote, complementary aspects in the sense that they account for equally important features of the light phenomena which can never be brought into direct contradiction with one another, since their closer analysis in mechanical terms demands mutually exclusive experimental arrangements, unquote. For an example, Bohr notes how the, quote, interference pattern would completely disappear if, in order to make sure that the light energy traveled along one of the two paths, the slits, between the source and the screen, we would stop one of the beams by a non-transparent body, unquote. That's a fancy way for saying, let's block one of the two slits and make it a single-slit experiment. Bohr is describing here single-slit versus double-slit interference phenomena. However, both phenomena are accounted for by wave mechanics, as I described in an earlier section. The light does not lose its wave-like properties when passing through a single slit. There's a great deal of evidence and papers and books that I can cite to this effect. Max Born, 1962, Ruckner and Peidl, 2013, Schrödinger, 1951, Young, 2023, and section 1.2 of my present paper, though that's not really evidence, that's just me summarizing evidence. Anyway, the particle-wave duality is far better demonstrated by single-photon interference phenomena, as seen in Ruckner and Peidl's experiment, which makes both aspects of light visible simultaneously, and arguably to an even greater paradoxical effect. There, before our eyes, a wave-like interference pattern is built up over time by an accumulation of uncannily choreographed photons. Richard Feynman puts it quite clearly, quote, "The electrons arrive in lumps, like particles, and the probability of arrival of these lumps is distributed like the distribution of intensity of a wave. It is in this sense that an electron behaves sometimes like a particle and sometimes like a wave," unquote. So there is no logical contradiction to the concept of a particle wave, but only a contradiction with previous empirical experience as to the expected behavior of particles and waves in the macroscopic world. The concept of a pilot wave, for instance, serves as a counterexample to the claim that the contradictions between experimental arrangements necessarily point to some contradictory ontology which transcends human epistemic categories per se. One of the pioneers of pilot wave theory, David Bohm, writes, quote, "In previously existing theories, only two possibilities were considered, namely that of the pure wave and that of the pure particle, these two possibilities being regarded as mutually exclusive. On the other hand, it is evidently possible that in any given process, both wave and particle could be present together in some kind of interconnection," unquote. The objections to Bohmian mechanics, i.e. pilot wave theory, do not concern its logical consistency, but rather its alleged mathematical inelegance or theoretical superfluity compared with the orthodox view, the Copenhagen interpretation. Regardless of whether Bohmian mechanics is correct, its existence as a coherent alternative to the orthodox view shows that the problems introduced by quantum mechanics, and most especially by single-photon interference, are not logical, but empirical problems. To conclude from an apparent contradiction between observables that the underlying beable transcends the limits of human knowledge is as unwarranted as concluding that the beable does not exist at all. Rather, a little imagination is called for. Section 2.2.1.2. The problem of measurement disturbance and the uncertainty principle. Regarding B, referring back to an earlier section, we might quote Bohr again. Quote, "It is impossible in any phenomenon for which the wave constitution of light is essential to trace the path of the individual light quanta without essentially disturbing the phenomenon under investigation," unquote. In other words, the only way to detect and confirm the location of a photon is to either absorb its energy into a detector, which removes it from play, or hit it with something else, which radically alters its state or its trajectory. It is simply not possible to track the trajectory of an individual photon beyond noting its source and its endpoint. Unobtrusive interaction with the object is impossible. In many classical experiments, this unobtrusiveness has heretofore been possible by means of the very photons we are now trying to study. I spy upon an amoeba by bombarding it with photons, refracting these photons with a lens, and then measuring them with my eye. This method works because the photons, being so much smaller than the amoeba, have no significant effect upon it. They are unobtrusive. But as the saying goes, who watches the watchers? What is small enough to unobtrusively interact with a photon itself? Writes Jung, not Carl Jung, but a different Jung who wrote a textbook in 2023, quote, classically, measurements are passive and can be done in a delicate way, so they simply reveal a reality which is already present, whether we observe it or not. Quantum mechanically, measurements play a much more active role and can change the state of a system. In particular, we shall see that if we observe a system in a particular state, we can't necessarily say that it was in that state before the measurement. Unquote. The situation seems bleak indeed, and yet Jung himself describes only a couple paragraphs earlier how, quote, electrons, being charged, readily scatter light so we can observe them by shining light, photons, on them, obtaining a flash every time an electron passes through a double-slit apparatus, for example. Unquote. The electron is not destroyed by the interaction. In fact, provided that the frequency of the light is sufficiently reduced, apparently an interference pattern still appears. The trouble is that this is at the cost of knowing which slit the particular electron passed through. Feynman, in 1964, though I know that's a bit of an older source, there was some confusion on that, but I'm referring to Feynman because Jung, writing in 2023, directly references Feynman. In fact, he doesn't just reference him, he says, go back and read Feynman because that's what I'm basing my comments in 2023 on. So if you have a problem with what Jung is writing in 2023, you can take it up with Feynman in 1964. And if what Jung is saying is, out of date, then maybe he shouldn't be writing textbooks for undergraduates, because this is where I got this from. So Feynman, in 1964, describes this limitation very clearly. Quote, it must be that the electrons are very delicate, and the light, when it scatters off the electrons, gives them a jolt that changes their motion. But maybe if we use gentler light, of a lower frequency, that is, or a longer wavelength, perhaps we can avoid disturbing the electrons so much. Yet, when we make the wavelength longer than the distance between our holes, the double slits, we see a big fuzzy flash when the light is scattered by the electrons. We can no longer tell which hole the electron went through. If an apparatus is capable of determining which hole the electron goes through, it cannot be so delicate that it does not disturb the system in an essential way. Unquote. So, to speak crudely, the more spread out a photon is, the less of a punch it packs, and so the less obtrusive it is in an experiment. With photons, greater spatial precision necessitates greater obtrusion via the photon's increased momentum. There is a little footnote that I make here that's worth reading to explain better what I'm saying here. Not unlike a spring, again, speaking very crudely here, so if you're a physicist and you're choking, then I'm sorry. There was some concern over me using this metaphor, and I'm using it anyway because it makes sense to me. So not unlike a spring, spatially contracted photons contain more energy than relaxed, spread out photons. This is due to the cosmological constants of the speed of light and the Planck quantum h. A beam of light moves at a constant velocity irrespective of the velocity of the different observers. The space-time of each observer warps in order to balance the equations out. This is the famous time dilation or spatial contraction of special relativity theory. Hence, c as a constant, the velocity of light. Also, the energy of a beam of light is divisible into units of h, i.e. into individual discrete photons or energy packets. The equation for photonic energy is E equals hc over lambda, where lambda is the wavelength. Thus, in order to alter the energy of a photon, only one variable is available for you to alter, namely wavelength, which is to say, very roughly, the size or the spread of the photon. Returning back to the text, consequently, as Feynman explains, quote, the jolt given to the electron is such as to change the electron's motion enough so that if it might have gone to where P12, that's a reference to a diagram of the interference pattern, P12 was at a maximum, it will instead land where P12 was a minimum. That is why we no longer see the wavy interference effects. In other words, the washing out of the interference pattern is, at the very least, explicable in terms of particle deflection. You're hitting the particles, and they're knocked out of what their original trajectory is going to be. That at least is a possible explanation which Feynman himself throws out there for why it is that when you use higher intensity light, in order to see exactly which slit it went through, it destroys the interference pattern. And because it destroys the interference pattern, you know where the electron is, but you don't know what its momentum is because you don't know the properties of the wave in which it was participating. I'll get into that a little more in a moment. Heisenberg extrapolated from this experimental inconvenience an epistemic limitation, his famous uncertainty or indeterminacy principle, namely that epistemic access to position is inversely correlated to that of momentum. But note that, contrary to popular belief, this is not due to an ontological complementarity or trade-off between position and momentum. On the contrary, it is precisely because momentum and position are positively related that our epistemic access to them is inversely related. Greater momentum means a more tightly constrained position, but also greater experimental obtrusion. It is not that momentum and position are themselves inversely related, but that increased momentum masks the position by its increased experimental obtrusiveness. And this is me speaking outside of the paper. Even that, so like with the photons, for example, presumably you know what the momentum is, because the momentum would be tied to the wavelength, to the amount of energy it has. So you already know that. And then when it bounces off of the electron, well, now you know where the photon is, because the photon is revealing where the electron was. So, I mean, in the case of the electron, there is a genuine masking because you can't know what the momentum of the electron is, because that's revealed by the interference pattern. As I understand it, you can't know that if you know the position, because in order to know the position, you have to hit it with a powerful enough photon. But that's an experimental inconvenience. And presumably, if you turned on the laser when the electron is passing through, before you turn on the laser or whatever it is that whatever light source you're using to detect where the electrons are, before you do that, it's going to produce a particular interference pattern. Great, so now we know the momentum. Then you turn on the laser, and that interferes and destroys it, creating the interference pattern, but that doesn't matter because the moment you turn off the laser, presumably it's just going to go right back to making the same interference pattern. So it's like, if there's problems with that reasoning, let me know if you're this far in the video, but you see my exasperation here. Moving on. Meanwhile, absolute certainty about a photon's position requires a position measurement, that is, the absorption of the photon by a screen. And as a little footnote here, I say the same goes for the electron, though its position may also be known in flight with a precision equal to the wavelength of the photon which was used to see it. See Feynman's example above. But although this destroys any information as to the momentum of that particular photon, this is when the photon is absorbed by the screen, the average momentum of the ensemble of photons which make up the interference pattern is itself displayed by the interference pattern. since photons of different wavelengths produce, in mass, different interference patterns, that is, different spacings between the stripes in the pattern, etc. The momentum at the time of measurement is thus implied by the interference pattern of the whole ensemble. In short, there seems to be some confusion about epistemic access in the conventional reading of the uncertainty principle. To a layman, it may be difficult to see just what all the ruckus is about. It looks like we can learn quite a bit about photons, albeit by indirect methods and clever strategies. The trouble arises only when we try to get some kind of a photograph or a video recording of an individual photon in flight. In that case, we must search for, example, some new particle, some sub-photonic particle with which we might retain positional precision without also disturbing the momentum of the test subject. Now, the uncertainty principle legislates against just this possibility, at least as it is commonly read. There is no subphoton or subquantum level that we might exploit to such an end. But upon what basis does this legislation rest? In my analysis above, it appears to rest upon an experimental inconvenience, that the obtrusiveness needed to measure a particle's position also precludes measuring that position very accurately. In other words, our tools are too blunt. But that is precisely what is at issue here. The question is not, how do we measure something so delicate with such blunt tools? To this, the uncertainty principle correctly answers, you can't, it's not possible. But rather, the real question is, are there any more precise tools that we have simply failed to discover yet? The uncertainty principle, when taken as an absolute legislation against epistemic access, appeals to ignorance or simply begs the question. Perhaps nowhere is the former made more explicit, that is, the appealing to ignorance, than in Feynman's own conclusion. Quote, "No one has ever found or even thought of a way around the uncertainty principle, so we must assume that it describes a basic characteristic of nature." Unquote. This is appeal to ignorance, which, if you're not familiar, it's an informal fallacy where you assert something positively based simply on the fact that there is no good evidence against it. Or in this case, you are asserting that the uncertainty principle must hold because we haven't refuted it yet. But we could always refute it in the future, so you can't make that certain of a claim. It's a purely inductive claim. As for the other, that is the begging of the question, David Bohm complains, quote, "The uncertainty principle's conclusions follow from the assumption, usually implicit rather than explicit, that certain features associated with the current formulation of the theory are absolute and final, in the sense that they will never be contradicted in future theories and will never be discovered to be approximations." Unquote. Grover Maxwell independently made a similar point to Bohm. Quote, "What shall we say about unobservability in principle? I shall begin by putting my head on the block and argue that the present-day status of, say, electrons is in many ways similar to that of bacteria before microscopes were invented. I am well aware of the numerous theoretical arguments for the impossibility of observing electrons, but suppose new entities are discovered which interact with electrons in such a mild manner that if an electron is, say, in an eigenstate of position, then in certain circumstances, the interaction does not disturb it." Unquote. While Maxwell admitted that, quote, "it is extremely improbable that we will ever observe electrons directly," unquote, he stood by his main point that, quote, "there are no a priori or philosophical criteria for separating the observable from the unobservable. We can talk about the possibility of observing electrons without committing logical or conceptual blunders, since any non-logical term is a possible candidate for an observation term." Unquote. In other words, there is no logical contradiction involved in the idea of observing quantum beables. The proposition that photons cannot be observed is not tautological, but contingent. The possibility remains, however remote it may seem at some given point in history, that future discoveries or technologies will make their observation possible. Now, it could still be objected that, even if there were subphotons with which we could bombard the photons without overly disturbing them, this would only defer the original mystery onto the subphotons. For the actual mystery represented by the uncertainty principle is that the ontological bottom floor of a mechanical system must remain, at least in certain crucial ways, epistemically inaccessible, precisely so that it may function as an epistemic key to everything else. But first of all, this is yet another a priori assumption based upon macroscopic mechanical intuitions. We simply do not know whether a subquantum level would pose this limitation. Again, the uncertainty principle is derived from experiment, not theory, and as such can only attain to logical contingency. The possibility always remains that, in the right context, the uncertainty principle would no longer be true. Second of all, the opposite position leads us into far more trouble. Let us assume that all observation requires some form of interaction, and furthermore, that all photons, or subphotons, are fundamentally changed by any interaction whatsoever. It follows that a completely isolated photon cannot be known, for as soon as something interacts with it, in order to observe it and learn about it, it instantly becomes a different sort of entity. Consequently, there is, ex hypothesis, no overlap between us and it, not even indirectly through something else, for that something else would also have to interact with it and change its nature. This is related to my point in section 2.1 that the quantum state cannot be said to exist under such conditions if any contact with it is sufficient to collapse it. It seems that a photon isolated from any interaction could very well exist as a little dancing gnome, which upon observation transforms into the more familiar forms observed in modern science. Such a hypothesis is, ex hypothesis, irrefutable, in much the same way as the Cartesian demon mentioned in section 2.1 of this same paper. There is, therefore, no reason not to study the forms which these little gnomes happen to consistently take when placed under observation and interaction, since there are, by definition, no conditions wherein their gnomish nature could concern us, for this would, again, require an interaction. Indeed, we may claim the most spectacular discrepancies between possible observation and unobservable reality, so long as the act of observation is guaranteed to collapse the unobserved state into an observed state which is consistent with a mathematical formalism. Before going on, I actually want to go back briefly to make a point about something. This is actually a little while back, earlier at the beginning of the section where I quoted Jung from the 2003 book. It's the final thing that he says that really kind of encapsulates the problem here. He says, in particular, we shall see that if we observe a system in a particular state, we can't necessarily say that it was in that same state before the measurement. Now, this is a remarkable thing to say, because I thought that the whole point here was that in order to observe something, you have to interact with it, and whenever you interact with something, you necessarily change its nature. So when he says we can't necessarily say that it was in that state before the measurement, that's incorrect. He should have said we can't say, full stop, that it was in that state before the measurement. There is no necessarily here. The word necessarily implies that there are times when the object is not disturbed by the measurement, by the observation interaction. If measurement necessarily disturbs the thing being measured, then we can absolutely say that it was not in this new state before measurement, right? But this raises the question, how do we know what state a thing is in before measurement in the first place, if measurement itself changes the thing? See, normally, So if I have like a bowling ball or something, if I hit it with a ping pong ball, technically speaking, the bowling ball moves. It just moves a very little amount. That's at least how I understand it, especially if they're like in space or something. But the fact it moves is, I mean, it changes the system, right? The bowling ball was at rest and now it is technically moving. The system has been changed. Well, I don't care. I already hit it with the ping pong ball, and the ping pong ball came back to me and told me where the bowling ball is, and it's technically no longer in that exact spot anymore. But again, I don't care. The ping pong ball hit the system. It changed the system, but the changing of the system didn't affect the ping pong ball. The ping pong ball's already gone. The ping pong ball's come back to me. So I got back the information from that interaction. But what epistemological anti-realism seems to be saying is that there is a change before the interaction occurs, right? Because if I throw the ping pong ball at it, it's as though the bowling ball knows the ping pong ball's coming, and it changes into a gnome, so when it hits it, I get gnome information back or something, right? Okay, well, maybe that's the case, but if so, then there is no way for me to ever know anything about the particle in itself in such a way that why even bother asking that question at all? It could be the case that everything I look at or interact with when I'm not looking at it either isn't there or is something else. But the moment I turn and look at it, as long as it will always turn back into the thing, then there's no difference. It's a useless skepticism. It could be a hippopotamus or a little dancing gnome, but as soon as a photon is close enough to the object I'm measuring, it reverts back into something else. So I just thought that that statement encapsulates everything that's wrong with this way of thinking, right? This whole notion of you disturbing the system and therefore we can't know about it is just, I don't know. I don't state it as strongly in the paper, but it just seems like complete nonsense to me. Anyway, let's move on. Section 2.2.2, Theoretical Limitations to Observation. Epistemological anti-realism claims that quantum beables cannot be known in themselves. This is more than a Kantian truism insofar as the observables obtained in different experimental contexts are held to be somehow mutually contradictory in nature, such that any attempt to synthesize from them an underlying beable must produce something incomprehensible to human beings and incommensurate with their faculties of knowledge. Contradictory observables can only be produced by transcendent beables. The notion of a particle wave, for instance, is considered to be as logically problematic as a square circle. Our mortal minds cannot comprehend these living contradictions and must reduce them to one or the other depending on our vantage point. Otherwise, I guess our brains will explode. I didn't put that in the paper, but you get how I feel about it. In Abbott's Flatland, for example, this is to kind of be more charitable to the position than my talking about exploding brains. In Abbott's Flatland, the two-dimensional flatlanders are limited to a one-dimensional perceptual horizon. Thus, they puzzle over passing spheres, which they can only understand as points which gradually expand and contract along their perceptual horizon. In the same way, observables might be understood as reductions of something transcendental into terms we can understand, this reduction necessarily forfeiting other information about the object. We need not appeal to differences in experimental apparatuses to make this point, and this would be inadvisable in light of the previous section. For an analogy of this problem is embedded in the very mathematical formalism of quantum mechanics. As mentioned in the introduction, section 1, a quantum object before the measurement event is treated as a superposition of multiple values at once, with each value assigned a probability of realization in the event of measurement. This superposition is encoded as a quantum state using complex numbers in the math. that is, combinations of real and so-called imaginary numbers. The problem is that these complex numbers have, because they involve imaginary numbers, no definite physical meaning. That is, they do not serve to index the superposed values with physical points in space-time, but only with an abstract vector space that is richer in its structure than the physical world. This is how I understand it. In other words, the amount of information necessary to describe the quantum state before measurement exceeds the amount of information that can be consistently assigned to the object as a physical object after measurement. Measurement is represented, mathematically, as an operation performed upon the quantum state, projecting it, as it were, onto a particular context of physical reality, which is represented, to use the terminology, as the eigenvalues available to that operator. This process necessarily destroys other information originally contained in the quantum state, but incompatible with the experimental context. It is for this reason that, as David Bohm writes, quote, "Among those physicists who first discovered the quantum theory, there was a rather widespread impression that the human brain is, broadly speaking, able to conceive of only two kinds of things, namely fields, i.e. waves, and particles. The reason generally given for this conclusion is that we can only conceive of what we meet in everyday experience. Thus, when we come to the microscopic domain, where, as we have seen, neither the field nor the particle concept is adequate, we are supposed to have passed beyond the domain of what we can conceive of. It is concluded that conceptual thinking will be restricted to the classical domain only, while outside this domain, the only thing left to do will be to engage in purely technical manipulations of mathematical symbols according to suitable prescriptions which it is the business of theoretical physicists to discover." Unquote. To quote Heisenberg himself, quote, "The experimental findings on the very small and very large scale no longer provide us with an intuitive picture, and we must learn to manage there without intuitions." Unquote. In other words, what is forbidden is to picture or visualize the photon. Any analogy a human being could come up with to understand a quantum beable must, according to this theory, necessarily be inadequate because of the impoverishment of our available experience, which is limited to the macroscopic or classical domain. This paternalistic proscription is justified on the grounds that laboring under false analogies and intuitions could lead researchers down blind alleys, and thus cause enormous setbacks in scientific progress. Specifically, the ban on picturization, or conceptual thinking, as Bohm calls it, arises for fear that the synthesis of observables into a coherent and intuitive picture might lead to mistaken inferences about further properties of photons based upon misapplied intuitions from the classical macroscopic world. It is easy to argue that, without an abandonment of intuitive picturization, Max Planck, for example, would never have adopted the discrete quantum of action as a tool to resolve the ultraviolet catastrophe. Nor would Bohr have developed his breakthrough model of the atom with its quantized orbits. I reply, however, that whatever the intent of the proscription, it nevertheless legislates a priori against picturization, and so bars, from the outset, the offering of counterexamples, such as Bohm's pilot wave theory. This is prejudice, almost by definition. Granted, Planck and Bohr made an anti-realist move by abandoning reality as they knew it in favor of the abstract reality revealed in their mathematics, but this only tells us that reality as they knew it was inadequate to reality as it actually is. This is not sufficient to prove that reality as we may someday know it will be similarly inadequate. Heisenberg's reasoning seems to be that his own inability to conceptualize a particle wave may be universally generalized to everyone else's conceptual ability. Surely, if Heisenberg cannot do it, then it must be impossible. It would be a waste of time for others to try. But this is to stifle the scientific method itself, which depends upon the generation of many wrong hypotheses before the best one can be found. Bohm admits, quote, "It is quite possible that we may encounter severe difficulties in such efforts to develop radically new concepts, that is, pictures, appropriate to the quantum mechanical domain. Nevertheless, the possibility of such difficulties can hardly be regarded as a good excuse for throwing up our hands in despair before any serious efforts in this direction have been made at all, and for asserting that our brains are simply not adequate to the job of imagining what we have not met in everyday experience or in experience in the classical domain." Unquote. Furthermore, to claim that prior to the inception of quantum mechanics, all scientific concepts were rooted in everyday experiences and natural intuitions is nothing short of laughable. The history of science is the history of the mutation and expansion of human conceptual paradigms. All that was intuitive or everyday to Thales of Miletus was not so to René Descartes, much less to Albert Einstein or Werner Heisenberg. The majority of the human population will readily testify that differential calculus, the backbone of classical physics, is anything but intuitive or derivable from everyday experience. In fact, its whole value consists in extending one's horizon of intuition by acquainting one with otherwise unfamiliar experiences, a remarkable process once known as education. There's a footnote here that I skipped over. Heisenberg effectively makes this very claim, the claim I was just arguing against, that prior to the inception of quantum mechanics, all scientific concepts were rooted in everyday experiences and natural intuitions. He basically makes that claim when comparing Einstein's theory of relativity with quantum mechanics. Quote, "Although the theory of relativity makes the greatest demands on the ability for abstract thought, still it fulfills the traditional requirements of science insofar as it permits a division of the world into subject and object, observer and observed, and hence a clear formulation of the law of causality. This is the very point at which the difficulties of the quantum theory begin." Unquote. Surely, such ominous claims would portend a revolutionary new metaphysics on Heisenberg's part that combines the subject and object in some way that we've never thought of before. Yet in the following paragraph, he only references epistemological limitations. Quote, "The uncontrollable perturbation of the observed system by an observation alters the values of previously determined quantities. There is no lower limit to the accuracy with which they can be known." Unquote. But I myself fail to see how Heisenberg's explanation justifies his intimation that the concepts of causality and objectivity break down at the quantum level. If anything, he relies upon these very concepts in order to draw his epistemic limitations. It is precisely because causality is continuous between the macroscopic and microscopic domains that uncontrollable perturbation is a problem, supposedly. I critiqued that earlier. And it is precisely because the microscopic domain is not so easily brought under our conscious control that we distinguish ourselves from it with terms like subject and object. So I just don't even know what Heisenberg's talking about. And by saying that, what I actually mean is I'm pretty sure I do know what he's talking about, but it's nonsense, and I'm trying to give him the benefit of the doubt. Anyway, setting my exasperation aside, Section 3, which is my conclusion and reflection. I shall now quote Heisenberg, to whom I have been rather unkind in this paper, especially in the last section, which makes it all the more ironically fitting that it is to him, of all people, that I owe the following excellent quote on the relationship of physics and philosophy. Quote, I believe that certain mistaken developments in the theory of elementary particles, and I fear that there are such, are due to the fact that their authors would claim that they do not wish to trouble about philosophy, but that in reality they unconsciously start out from a bad philosophy, and have therefore fallen through prejudice into unreasonable statements of the problem. One may say, with some exaggeration, perhaps, that good physics has been inadvertently spoiled by bad philosophy." Unquote. The great irony here, of course, is that I would say pretty much all of that, perhaps, to Heisenberg and perhaps even Bohr. It is my judgment that Heisenberg's generation in physics have themselves dug us deeper into a rut of bad philosophy, and it shall perhaps take equally Herculean efforts to finally dig ourselves back out again. I do not say this casually. 4 years ago, when I began my present foray into quantum physics, I expected, and even aimed, to become a champion of the bold new philosophy I saw incipient in the work of Bohr and Heisenberg, and so strenuously opposed by Einstein. But to my own surprise, I now find my stance, if not rotated a full 180 degrees back towards Einstein, then perhaps at least a good 90 degrees away from both of them. Heisenberg I can take or leave, but Bohr presents me a greater challenge. If I have seemed harsh against Bohr in this paper, it is only because, to reverse Nietzsche's adage, quote, "It is a subtle and at the same time noble self-mastery, given that one wants to criticize at all, to only ever criticize where one really is in agreement," unquote. And in what are Bohr and I in agreement, at least in my estimation? I take this to be, on the one hand, a love of the strange, the unexpected, and the new, combined with the hunch that the traditional classical model is inadequate, not in specifics, but at its philosophical foundations. I believe that Bohr and I share an expectation that the deepest problems are not solved in the same old way, but demand of us a new way of thinking, a new philosophy. But the new philosophy which seems to have been introduced by Bohr, Heisenberg, Born, and others, a philosophy rooted in anti-realism, as I've defined it in this paper, is gravely mistaken, as I hope to have shown above. Part of the reason for its ascendancy seems to be the conflation of thoroughgoing anti-realism with mere skepticism, and many more people are ready to be skeptics than actual anti-realists. To attack anti-realism is thus to risk the ire of precisely those whose beliefs would otherwise recommend neutrality on this issue. On the other hand, my active rejection of anti-realism does not necessarily mean that I embrace the usually mechanistic determinism implicit in the realism of Einstein, Bohm, or Bell, or Maudlin for that matter. At present, I am inclined to reject Bohr's anti-realism, but preserve what I'll call his indeterminism, while rejecting Einstein's determinism and preserving his realism. How, or whether this could be done, is the topic for future research. Thank you all for listening. It's been quite a journey writing this and presenting it, and then presenting it to you guys. So if you're at this point in the video, I would very much like to know what you think of the ideas I've presented, what made sense, what didn't make sense, where do you think I'm wrong, etc., because this is stuff that I would like to continue working on in the future. And I will admit that this is sort of the beginning of me trying to challenge an attitude that I think is very prevalent in science right now and that I think is causing a lot of problems. But to challenge it in such a way that I can preserve the things that I think are very good in certainly in Bohr's treatment of these problems. So yeah, that's sort of where I'm heading in the future with this stuff anyway. So thank you for listening, and thank you all for your support. I really do appreciate it. And I will see you all in the next video.